I'm Divyansh Ameta and I'm along with my friend Jayesh Bankoti. We are going to present a small video on the aerodynamics of projectile motion and shape refinement of a projectile fin.
So friends, let's start with projectile motion, its introduction and its governing equations. Motion in the ideal case without air resistance. For getting these results, first of all we will require the three known Newton's equations of motion. So which are the final velocity equals to u plus at, the distance traveled equals to ut plus half at square, and the final velocity and the initial velocity. There is a relation of v square equals to u square plus 2as, where the s is the distance. So using these three results, we get the range of the projectile motion in ideal, or we can say the motion in which there is no air resistance. Here, the range is v square plus sine through theta by 2g. This g is the gravity and theta is the angle of inclination of the throw. Time of light is 2u sin theta by g, whereas the y max, or the highest height achieved by the ball, is u square sin square theta by 2g.
Case of projectile motion considering air resistance. For this, first of all, let's get acquainted with some of the terms. Drag force. Drag force is the force due to air resistance that a projectile experiences. It is directly proportional to the square of velocity of the projectile at that moment.
So friends, let's introduce you to the second most important term, terminal velocity. So what is terminal velocity? Whenever a ball is falling, it attains a velocity, namely let's take it to be v. So there is a drag force that is proportional to v square. Let the proportionality constant be k. So the drag force applying on this ball is kv square, and hence in the opposite direction the weight applied is mg. When mg is equal to kv square, the v, as you know, as mg will be equal to kv square, the total acceleration, that is mg minus kv square, the total a will be 0. Hence, as the total a is 0, the velocity attained will be constant, and this constant velocity in which the ball falls is the terminal velocity.
Now let's look at the equations. Drag is equal to half CD is the coefficient of drag, rho is the gas density, A is cross sectional area, and Vt is the terminal velocity. So drag is equal to half CD rho A into Vt square. So to calculate Vt, we equate mg and drag. So the terminal velocity comes out to be under root 2 mg upon CD rho A. So this is our terminal velocity. Now let's put this. So now let's come to the Newton's equations of motions again. F is equal to ma is equal to minus mg into minus drag, half cd a rho into v square. So the acceleration comes out to be minus g into 1 plus v square upon term. So our acceleration came out to be minus g into 1 plus v square upon vt square. We know acceleration can be written as dv by dt. So we have a differential equation in terms of v and t. Let's take this t this side and this 1 plus v square upon vt square this side and integrate. After integrating, we get v upon vt is equal to v naught upon vt minus tan of gt upon vt upon 1 plus v naught upon vt into tan of gt upon vt.
So now using this equation, we will try to find out the highest point of the trajectory. Now at this point, the vertical velocity, or here the v that we have used, will be 0, and we will try to find out the time at which the v is 0. So using this equation, we will put v equal to 0, and then we will derive to the time that is equal to vt by g into tan inverse v naught by vt. Now this is the time at which ball reaches the topmost point where v, our vertical velocity, is 0. So now let's try to find out the highest point, or the highest point attained, the y max possible for the projectile. So we will use the acceleration, that is dv by dt equals to minus g 1 plus v square upon vt square. Okay, we'll use this as our basic equation. Now this is the acceleration. Using chain rule, we can write the acceleration to be equal to v dv by dy, because a is dv by dt, which can further be changed using the chain rule and can be derived to the final result as v dv by dy. Hence, using this equation and integrating it both sides, we'll get an equation between v and y, where y is our vertical distance from the ground, and we will get a log function. That's a basic thing. And going further, integrating it and using and plugging the velocity at the 0, which is the highest point, we'll get the location of y. And at the highest point, the y, where the velocity is 0, will be equal to vt square upon 2g into ln v0 square plus vt square upon vt square. As you can all see, there is a great difference between the ideal equations of y max, which was u square upon sine square theta by 2g, and this equation. There is a great difference. And why is this happening? As you can see, there is a difference in the actual path and the ideal path calculated by us, because in actuality, because of the air resistance, there is not a true parabola forming. So we found out the equations of the projectile with air resistance. But in all these equations, we have assumed it to be a point body object. But now let us look up to these bodies in like a solid bodies. So for doing the solid body dynamics, we will require some key terms.
There are three basic types of motion associated with the projectile. For example, if this is the projectile, the motion along this transverse axis is called roll motion. The motion along this axis is called yaw motion, and the motion along this axis is called pitch motion. Now let's see how these motions affect our projectile motion. First of all, yaw motion. Due to yaw motion, the projectile deviates from hitting the target in transverse direction. Due to the pitch motion, the projectile will fall either near or far away from the desired range that we obtained in the ideal case. And due to the roll motion, it will again deviate from the target in the